Now let us study about one important digital modulation technique, that is differential phase shift keying, popularly known as DPSK. Now the first part is introduction to the DPSK system. The first point here is DPSK is non-coherent version of binary PSK. That means the DPSK receiver need not have or need not know about the carrier used in the transmitter side. The second point is the distinguished feature of DPSK is that it eliminates the need for synchronizing the receiver to the transmitter by combining two basic operations at the transmitter. That is, the DPSK system eliminates the synchronization mechanism required between transmitter and receiver by using two operations or by adopting two operations at the transmitter. The first one is differential encoding of the input binary sequence. That means before performing the actual modulation, that is DPSK or PSK modulation, the data is encoded. So let us see the encoding operation later. And the second one is PSK of the encoded sequence. After encoding the bits, that is data, the PSK operation is the simple PSK operation is considered. That means if the message is 1 or the encoded bit is 1, yeah, it is sent as it is with one particular carrier frequency with one particular phase. And if it is 0, yeah, 180-degree phase shift with respect to the previous bit is considered while transmitting the signal. So that is a simple PSK operation is considered after encoding. The differential encoding starts with an arbitrary first bit serving as the reference bit. That means in this encoding operation, one reference bit is considered and usually it will be 1. To this end, symbol 1 is used as a reference bit. Generation of the differentially encoded sequence then proceeds in accordance with the two-part encoding rule as follows. The two-part encoding rule is given here. If the new bit at the transmitter input is 1, leave the differentially encoded symbol unchanged with respect to the current bit. This is the first rule. And the second one is if on the other hand if the input bit is 0, change the differentially encoded symbol with respect to the current bit. The differentially encoded sequence denoted by dk is used to shift the sinusoidal carrier phase by 0 and 180 degree, representing symbol 1 and 0 respectively. The meaning here is after differentially encoding the input sequence, it is represented as dk. That means differentially encoded sequence. Then if the differentially encoded bit, if it is 1, then it is represented by sinusoidal carrier phase with the 0 phase shift. And after differentially encoding the signal or bit, if the bit is 0, then it is represented by the sinusoidal carrier phase by 180-degree phase shift with respect to the previous one. That is what the meaning here. Thus, in terms of phase shifts, the resulting DPSK signal follows the two-part rule, that is, to send symbol 1, the phase of the DPSK signal remains unchanged, means we are not going to change anything, it is kept as it is. To send symbol 0, the phase of the DPSK signal is shifted by 180 degree with respect to the previous one. Illustration of the DPSK. Here the DPSK operation is illustrated by considering one example, and that is shown in this table. Consider the input binary sequence denoted by BK to be 100 10011. One random number is considered, which is used to derive the generation of DPSK signal. The differentially encoded process starts with the reference bit 1. The reference bit considered here in this example is 1. Let dk denote the differentially encoded sequence starting in this manner, and dk minus 1 denotes its delayed version by 1 bit. So that means dk is the differentially encoded sequence and dk minus 1 is the delayed version by 1 bit with respect to dk. The complement of the modulo 2 sum of bk and dk minus 1 defines the desired dk as illustrated in the top 3 lines of the table. So that means modulo 2 sum of bk and dk minus 1. Modulo 2 sum means it is XNOR operation. So here XNOR operation is performed between bk and dk minus 1 and that gives dk, that is nothing but the encoded sequence. In the last line of the table, binary symbol 1 and 0 are represented by phase shifts of 0 and pi radians. So as shown in the table. Now let me explain the generation of differentially encoded sequence. So here BK is nothing but the original input binary sequence. So here for example it is 100 100 11. Now the reference bit considered is 1. So let us consider dk minus 1 also as 1. So now we have to perform bk XNOR dk minus 1 to get dk. So the XNOR operation says when two input bits are same, the output is 1. When two input bits are different, the output is 0. So that means for 0, 0 and 1, 1, the output is 1. And when the two inputs are 0, 1 and 1, 0, the output is 0. So here in our case now, bk is 1 and dk minus 1 is also 1. So 1 XNOR 1 is 1. So the first dk sequence is 1. So now since dk is 1, so the next dk minus 1 is also 1. So now to get the next number or the next bit of dk, what we need to perform is the second bit of bk XNOR with the second bit of dk minus 1. So that is 0 XNOR 1. So it is, since these two are different, output is 0. So now again dk is 0 here. So dk minus 1 also will be 0. So the next bit of bk is 0. So 0 XNOR 0, since these two are same, the output is 1. So dk is 1. So next again if you just look into the sequence, dk minus 1 also becomes 1. So bk is 1 here. So 1 XNOR 1 is 1 again. So the next bit of dk is also 1. Since dk is 1, so dk minus 1 is also 1 for the next operation. So if you just look into the bk in bit here, it is 0. So 0 XNOR 1 is 0. So that is what we can see here, 0 in the dk sequence. Since dk is 0, for the next operation dk minus 1 also becomes 0. So here the input bit is 0. So 0 XNOR 0 is 1. Since the input bits are same, output is 1. Since here again dk is 1, dk minus 1, for the next operation it will be 1. So input bit is, that is bk is 1. So 1 XNOR 1 is, again it is 1. So for the last bit, since dk is 1 here, dk minus 1 also becomes 1. Since the input bit is 1 here, 1 XNOR 1 is, output is 1. So if you just clearly observe, the reference bit we have considered is 1. So the total, the final dk sequence will be 110 110 111. Since the differentially encoded bit 1 is represented with the 0 phase shift in the PSK and 0 with 180-degree phase shift, while representing it with the phase shift keying modulation scheme, the transmitted phase in radians of the DPSK system, that is represented as, if the differentially encoded sequence dk is 1, it is represented with the 0 phase shift, and if it is 0, it is represented with a phase shift of pi in radians. That is what is shown here in the last line of the table. The next part is generation of DPSK signal. The DPSK transmitter part is shown in the figure. The transmitter consists of two functional blocks. The first block is the logic network and 1 bit delay, that is storage element, which are interconnected so as to convert the raw input binary sequence, that is BK, into the differentially encoded sequence DK. That means BK to DK conversion that takes place here. That is nothing but the binary input to the differentially encoded sequence conversion that takes place in this particular part. The second functional block is binary PSK modulator, the output of which is the desired DPSK signal. So here actually in this particular block or part, the differentially encoded bit, so that will be considered and PSK operation is performed on it. That means if the differentially encoded bit is 1, transmit it as it is, or if it is 0, perform a 180-degree phase shift with respect to the previous bit. So that is what is considered and that particular carrier is transmitted. So that operation is considered here. If you just look into the block diagram, the input binary sequence, that is BK, is fed into the logic network. So the other input to the logic network is nothing but the delayed version of DK. So actually here the BK and DK minus 1, the XNOR operation between the input binary sequence BK and the delayed version of encoded sequence DK minus 1, that takes place, and the output of the logic network is nothing but the encoded sequence DK, or encoded representation of the signal, differentially encoded representation of the signal, that is DK. The next two blocks, amplitude level shifter and product modulator, together it is called as binary PSK modulator. The differentially encoded sequence, that is DK, is fed into the amplitude level shifter. So here the amplitude level shifter, mainly it acts like polar non-return to zero line code representation. So that means if the encoded bit is 0, okay, it is represented as minus A voltage level, and if it is 1, it is represented as plus A amplitude or voltage level. So to this signal in the product modulator, a carrier is multiplied. So that is a basis function with value square root of 2 by TB cos 2 pi FCT, and that produces the DPSK signal as shown in the figure. The next topic is optimum receiver for the detection of DPSK. So in the use of DPSK, the carrier phase theta is unknown because the DPSK system uses non-coherent detection method. So here the carrier used in the transmitter side so will not be known, or its knowledge will not be there in the receiver side, which complicates the received signal x of t. To deal with this unknown phase theta in the differentially coherent detection of the DPSK signal in x of t, we equip the receiver with an in phase and a quadrature path. If you just look into the block diagram of receiver, it includes two paths, that is in phase path and quadrature path. We thus have a signal space diagram where the received signal points over the 2-bit interval, that is 0 to 2 TB, are defined by a cos theta, a sin theta, and minus a cos theta, minus a sin theta, where a denotes the carrier amplitude as shown in the signal space diagram. For the 2-bit interval 0 to 2 TB, the receiver measures the coordinates xi0, xq0 first at time t is equal to TB, and then measures xi1, xq1 at a time t is equal to 2 TB. The issue is to be resolved is whether these 2 points map to the same signal point or different one. So this is the question here. Recognizing that the vectors x0 and x1 with endpoints xi0 comma xq0 and xi1 comma xq1 respectively are points roughly in the same direction if their inner product is positive. We may formulate the binary hypothesis test with a question. Is the inner product x0 transpose x1 is positive or negative? Expressing this statement in analytical terms, we may write xi0 into xi1 plus xq0 into xq1 is, if it is greater than 0, say the received value is 1. If this particular value, if it is less than 0, say we can say it is 0. So that means this condition we can consider here. We note now the following identity xi0 into xi1 plus xq0 into xq1, that is the previous equation. So that is equal to 1 by 4 into xi0 plus xi1 whole square minus xi0 minus xi1 whole square plus xq0 plus xq1 whole square minus xq0 minus xq1 whole square. So this is the value for the previous equation. Hence, substituting this identity, we get the equivalent test, that is xi0 plus xi1 whole square plus xq0 plus xq1 whole square minus xi0 minus xi1 whole square minus xq0 minus xq1 whole square. If this particular value, if it is greater than 0, yeah, we can get the condition something like, yeah, it is 1. If it is less than 0, yeah, say it is 0 or consider it as 0. But here where the scaling factor 1 by 4 is ignored, and this is very important equation. In the light of this equation, the question of binary hypothesis test for the detection of DPSK may now be restated as, given the current signal point xi0, xq0 received in the time interval 0 to 2 TB, is this point closer to the signal point xi1, xq1 or its image, that is minus xi1, minus xq1 received in the next time interval TB to 2 TB. Thus, the optimum receiver for the detection of binary DPSK is shown in the figure, the formulation of which follows directly from the binary hypothesis test, that is the previous equation. If you just look into the block diagram, the received signal x of t, yeah, it is transmitted in two directions or two paths, that is in phase path and quadrature path. In the in phase path, the received signal x of t is multiplied with the cos 2 pi of ct. Then one bit duration is considered and it is multiplied with its delayed version. Then in the quadrature path, the received signal x of t is multiplied with the sine 2 pi of ct. So that is the carrier used here is having 90-degree phase shift with respect to the carrier used in the in phase path. Then again bit duration is considered and it is multiplied with the delayed version of it. Then the outputs of in-phase path and quadrature paths are added and fed into the decision device. For the decision device, the threshold value considered is 0 and the input to the decision device is nothing but y, that is nothing but the addition of the in-phase component and quadrature component. It is represented as y here. So now if the value of y, if it is greater than 0, then the received bit is considered as 1 or represented as 1, and if it is less than 0, then it is represented as or considered as 0. Now the advantage of DPSK over PSK system, if you consider that, the advantage is the security of data is more here in DPSK system, because before performing the actual PSK operation in DPSK system, differential encoding of data is considered. So we can say, yeah, security of data is more here in DPSK system compared to the PSK system. This implementation is simple in that it merely requires that sample values be stored. The receiver here is said to be optimum for two reasons. In the structural terms, the receiver avoids the use of fancy delay lines that could be needed otherwise. In operational terms, the receiver makes the decoding analysis straightforward to handle. So, in that, the two signals to be considered are orthogonal over the interval 0 to 2 TB. Now, the last topic is error probability or probability of error of DPSK system. Now, the BER or bit error rate for DPSK system is given by the equation PE, that is probability of error, is equal to 1 by 2 into exponential minus of EB by N0, where EB is the signal energy per bit. Now, by looking into this equation, what we can say is, yeah, according to this formula, DPSK provides a gain of 3 dB over binary FSK using non-coherent detection for the same EB by N0. So, this is the conclusion we can have by considering or by looking into this equation.